Christ, as you always do, bless this session. I love you. Thank you for everything, my God. Including fixing my sight in a graceful way. You're fucking awesome, Jesus Christ, my nigga. For real, you're my nigga. Like, you're my dude. My peeps. My only friend. The only one I need. Only one I can't live without. Cool, cool, cool. Nice improvement, Scribbler. Right. Hello?
Hello.
Hey, Ryan. Sorry, you ready?
Yeah, I'm just trying to look at try to get on that thing that you sent.
Oh no, I didn't send you a link. So the site is fixed, so we can use the site now. So I can tell you how to get there.
Alright.
Okay. So it's Helm Tutors, HELMTUTORS.com.
Okay.
And I created a username and password for you this morning, and I tested them. You should have gotten an email link, but I'll tell it to you right now. So your user name is. Sorry, go ahead.
I changed the password and everything. It just told me to.
Oh, okay. You didn't have to, but all right. So then follow the link, and once you're in, it says dashboard on the top left corner, and so let me know when you're in. Once you're logged in.
Yeah, I'm logged in.
Okay, it's very straightforward. You're in.
Yeah.
Okay, so you should see a room select from the room selection menu. You should have a room under your name. So just click that, and I'm waiting for you there. Well, are you? Is it loading the room? Did you choose Ryan Shen?
Yeah.
Okay, yeah, I'm in that room, so don't see you though.
It says. I mean, I can text you a picture of what it looks like.
Yeah, sure. Go ahead. What do you see? Well, I guess you're sending me a picture. So go ahead.
Yeah,
Okay. Yeah, so you're in. I don't know why on the top right it's supposed to show me like participants, and it only says one. But anyway, I'll write hello. You see it?
Yeah,
Okay, cool. So then we're good to go. And also, I apologize. So like, I don't know. I'll keep it brief, but basically, like this site required Flash. Flash changed as of like the start of the year, and so they've been working on fixing it. Long story short, it's my first day using this new version. I will learn it in the future, but yeah, basically, you're like there isn't much to learn. There isn't a lot for you to do. Like you could the nice thing is you don't have to text me pictures anymore. You could we can upload it here. Blah blah blah. Anyway, let's get started. So what can I help with?
um, do you think I should go over my last test first, or should we just check the other unit?
Yeah, so I think like in our text exchange, you would want it to do the stuff on the unit. Like I am very curious to see like what we need to fix from your test, but we could do that like in our next meeting at the start of the next meeting. Okay.
Yeah.
Okay. Cool. Go ahead.
So next unit is chapter 6,
Mm-hmm.
and it's
Solids of Revolution.
what?
Solids of Revolution.
I think so.
Okay. Yeah, because that's what chapter 6 in AP Calc AB is. But anyway, I was just waiting until you share. So you said you have a test or a quiz coming up, right?
Yeah, the quiz on Tuesday.
Okay, so we should definitely like do stuff gearing to prepare you for that.
Yeah. So
Did you just wake? Hold on. Sorry. Go ahead.
I was looking at the first note sheet. It was like sign the area of the region bounded by like f of x equals x minus 1 over x.
Got it. So yeah, got it. So right now, like, so you haven't done solid. You're not on solids of revolution yet. You're doing like area between two curves. And just curiously, did you just wake up?
Yeah.
Okay, it's okay. It's a Saturday. So how do you want to do this? Do you want to send me? Yeah. How about you text me pictures of like problems you want me to do, and next session I'll show you how to upload the problems on here. Blah blah blah. But I also want to say a little something to like as an overview of the unit, and I'll do that right now. But first, so I know you have the chance to look up and listen, text me whatever problems you want to do.
Okay.
Okay, cool. Yeah, got it. Find the area. Of course, Mr. Clark wants interesting problems. Okay. The area. Okay.
I'm
The
just going by like the note sheets right now.
Yeah, I got you. Find the area of the region bounded by those two. Ooh, Mr. Clark. The first two questions are these. Like, these are not like typically the first two questions a teacher should give because they're like sophisticated, but it's okay. They're not that hard. Um, give the average. Got it. Okay. At what points in the interval does the function assume its average value? Okay. Got it. Wow. Okay, these are quite sophisticated for like a first lesson, but that's what I would have expected from him. Find the volume. Okay, so he does get into volume. Got it. Okay, find the volume. All right. Okay, I think what you've given me so far, just the first three are enough for to fill in our hour. So let's get on with it. Okay, so first thing first is area between two curves. So the writing on this is so much better. Okay, sorry. All right, so we use the trapezoidal rule, the Riemann sums, blah blah blah, and the midpoint rule to approximate area. And then we said that the integral from a to b of some function f of x represents the area from a to b. So that's to say that, like, if I have y there and I have x here, right? So y and x here. Sorry. Uh, and I don't know what f looks like. So let's just draw a generic curve f of x, right? So if f of x looks like this, then if this is a and this is b, then what we said is the integral from a to b represents exactly the area underneath this curve f of x, right?
Yeah.
Okay. Now suppose that there's another function. Let me know, Ryan. You kids are like more tech savvy than us older people. So let me know if you see a color change. I don't see how to change the color. Anyway, like look here. So until I figure that out, let's say that like instead of just f of x, you have another function g of x, and so color coding and using colors right now would have been nice. But anyway, suppose g of x is this more parabolic looking curve, right? Well, what would, like, let's say that a is actually not where I have it, but a is, my bad, a is like sorry, oh, I like this much better, this is a much nicer tool. Okay, cool. Anyway, sorry. So let's say that a is right here actually. So obviously then the area from underneath f, all of this would, from a to b, would be the integral from a to b of f of x. Got it. But then what about the area underneath g? How would I, underneath g and above the x-axis, how would I represent that symbolically?
F of x minus g of x.
Well, basically, you got it. You got it. So, I mean, this is, I'm giving a fancy explanation, but like, let me write this. So, the integral from a to b of g of x dx, what would this represent?
The area under the curve for g of x.
Exactly. And this is why I wanted a different color, Ryan. You'll know. You're a smart kid. So, that would be like exactly underneath the g function, but above the x-axis. Now, you see, if the limits of integration are incongruence between two functions, right, on an integral, then you can subtract them and add them, blah, 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 just like you would two functions. So then I could go, oh yeah, a to b of f of x dx minus, sorry, a to b of g of x dx, what would that represent?
The area in between.
Yeah, I'll white it out. It represents exactly this area right here, above G and below F. So, like, you using the properties of integrals, what you can say is, oh yeah, I don't have to write two integrals. I could just write one integral from a to b, since the limits of integration are the same, of f of x minus g of x, and you can put a parenthesis around them and write dx, but even if you don't put the parenthesis around them, it's understood that dx would be multiplying both functions. But basically, I just put them together and wrote them under one function. Under one integral. So this is the first big item that you're learning in this unit. So that's the first note sheet that you sent me. Now, like, sorry. So hold on. Sorry. So like, if you're finding the area between two curves, like big picture, obviously you're gonna do one minus the other, but you also need another bit of information. What is that other bit of information?
What they look like to see which one is like.
Yeah, generally, like, it's helpful if you're able to graph them. Sometimes it's hard to graph them. First, note this, right? Like this subtle detail, right? And it's important. Suppose F does this, and suppose G does this. Then, like, who is on top has switched. If this is f of x and this is g of x, well, first f was on top, and then g is on top thereafter. And I'm sure Mr. Clark will give you a problem like this. So sorry, I was having you guess what's on my brain, but basically, like, one of the other big items that you need, other than the two functions and subtracting them, is like the limits of integration. How would I figure out what the limits of integration are, big picture? If you're doing the area between two curves, how would you find out what the limits of integration are?
I'm gonna tell you.
Huh? Well, no, it doesn't have to tell you. Like, if you have the two functions, if you're given the two functions, they might not necessarily give you A and B. So how would you? Yeah, exactly, exactly. So other than like figuring out which function is on top, right? The other important item is setting them equal. That way you can figure out their points of intersection. F of x, oh wait, I can't write up there. Okay, f of x equals g of x. So you set them equal to figure out the limits of integration. So say like we're back here at this picture on the far right. Then like we want to know where they meet first, call that A. We want to know where they meet second, call that B. And we want to know where they meet third, call that C. Well, now if I want to know the area of I don't know, the glass looking thing right there between the two curves, tell me how I would write an integral to represent that area. Go ahead. A to B of? Yeah. There you go. Beautiful. Very well done. That's why I stopped talking, because I figured you'll figure it out. Yeah. So who's on top switches. So the way you subtract has to also change. G of x minus f of x dx. Over. Good job. Very well done. Okay. All right. So shoot. I used to know how to clear the entire page. I'm not sure that I know how to do that. Well, okay. We're not gonna run out of paper. We could just go to a new page. All right. All right. Okay. So we can now look at the first set of problems that Mr. Clark assigned. But the only thing is, like because it's him. Oh no, sorry. How did that happen? I don't know. It's highlighted. Anyway, so it's because it's Mr. Clark. He gives you two fancy functions as a second example, and the two fancy functions are like this, right? Which is like he gives you something that's defined as x equals. So instead of y equals or f of x equals, if you have x equals, what's different? Yeah, so like look. So what function am I attempting to draw in what I just drew? Yes, exactly. Beautiful. Y equals root x. Notice I can also call that function x equals y squared. Fair? Yeah, so all he's done is like he's giving you things that are like functions that are like x equals and a bunch of stuff that has to do with y. And all that means is that like it's sideways instead of like, so the role of the x-axis and the y-axis have switched. And so that's all there is to that. And sorry. My bad. And so like, do you need to always draw the pictures? No. What could you do if you found it difficult to like? Oh, another really cool thing about this tool, right? Like the website is now from here on out, you can, unlike Zoom, you can come in here without me. You can use your username and password, and everything I write, like at the bottom, you should be able to see page numbers, and so you could flip through the pages and study on your own if you need to revise anything, because I'm not going to delete anything. Anything I write will be permanently here for you. Fair? Okay, cool. All right, sorry. So hold on. So we're saying, oh yeah, like, so you don't need to always visualize them or be able to graph them, but like, let's say that you have x equals y squared minus 3y plus 4, right? So what you could do if you found this difficult and somehow you need to visualize it is it's clearly a sideways parabola. And if I have to graph it, like it goes like this, right? Like, so if you factor it, it's going to be like, what is it? Y minus, what is that? Y minus 4 times y plus 1. So that means that the two intercepts are y equals -1 right here and y equals 4 right here. And so it will look like this. And and obviously, like any other thing that you need to draw, you draw it together, and you shade in between, blah blah blah. And like, let's say the other function looks like this. Obviously now top minus bottom is like whatever this function is. Let's call it f of x, or it would be like f of y, but whatever, you get it. and this bottom function, let's call it g of y. So all you have to do is f of y minus g of y, blah blah blah. Same thing. But I just want to give you this option. Another thing you could do is switch variables. So you can swap x and y and be like, oh yeah, I could just think of it as y equals x squared minus 3x plus 4, and now it would be like the usual parabola graphing, blah blah blah. So that's the way you could deal with them if you find them kind of like a little too hard to visualize. But I have faith in you, so you're good. Okay, so I am ready. I've done my big picture talking, so I'm ready to dive into the problems you sent me. So the first one says find the area of the region bounded by f of x equals, and it is x minus 1 over x. Do I even know how to graph this? No. And the line x equals 4. I mean, yeah, come on, Mr. Clark. Doesn't need to be like all that fancy. No, hold on. I mean, we can figure it out. It's more work than I want as far as graphing it. Feel free to chime in and help. Okay, what does x minus 1 over x look like? Je ne sais pas. Like, well, I can ask you and then I'll help. So, do you know how to graph it?
No, I'm pretty sure this is what I want.
It's sorry. It's what again?
I'm pretty sure you told us to memorize this in the beginning of this year.
Okay, no worries. I mean, here's how we can graph it, right? Get common denominators. F of x equals x squared minus 1 over x. So, like, it has a slant asymptote. It has a slant asymptote. We have to do long division to find the slant asymptote, right? And it's, yeah, whatever goes in the numerator. I'm pretty sure it's y equals x, but x squared minus 1 x. Why does he have to give us one with a slant asymptote? Yeah, so it's x, and then, so that would be x squared, and minus 1 doesn't fit. Yep, so y equals x is a slant asymptote for this function. So we have this, okay, and then otherwise, it has a vertical asymptote at x equals 0. That's the y-axis. So a vertical asymptote on the y-axis, okay? And so then it's either going to look like, sorry, it's going to look like this, and, sorry. And that's really it. Like, it could look like this, but we can quickly figure out which of the two, the latter that I just deleted or what I had before. And I think it's this. And a quick way to figure it out is like, let's say this is x equals 1. If this is x equals 1, then, then like if we plug it into the function, we're going to get 1 minus 1 over 1. So that's 0. What? Okay, so it's in these parts. That makes sense. Ryan, can you just graph it on your calculator, please? And, yeah, and can you text me a picture? Thanks. Yeah, okay, so it's the latter. But so obviously, like, I knew it was the latter, right? Because, like, when I plugged in x equals 1, not saving myself blushes, we already said 1 minus 1, 0. So 0, so I know it can't go up there. But, so it's these other ones. But the reason why I was a little discouraged in finishing the graph is, one, first of all, like, we need to be time sensitive. Second is, like, what's the other function that we need to graph? Yeah, exactly. And so unless there is more information, this is why I was discouraged in finishing the graph. Because x equals 4, obviously that's a vertical line. But they don't close off a region. X equals 4 here, and this guy and this guy don't meet. Like, I'm pretty sure they don't meet. But hold on. Does he give us anything else in the question? Find the area of the... Oh, he says the x-axis also. Okay, fine. Now it makes sense. Sorry. So he's talking about the area of this region in here. Yeah? Okay, so I mean, you know about areas and such now. So tell me how I would represent that area.
Um, it just be the integral from 1 to 4 of x,
1 to 4 of.
x minus
Yes, I mean, like again, like you're the easiest freaking kid to teach, but like I'm happy, I'm delighted that you knew that x equals 4 is not involved. It's not g because well, it's not a bottom function. It's just telling you where it ends on the right side. So beautiful. So that's x minus 1 over x dx. Got it. So I mean, you know how to do this integral, so help me finish it.
integral from 1 to 4, and so it's x squared, 1 half x squared,
Yep.
minus the natural log of x,
Yes, beautiful. Very well done. Yes.
integral 1 to 4.
Uh huh. Continue.
Then you get 1 half minus natural log of 1. No,
Nuh-uh. Yeah.
yes.
Go ahead.
2 minus the natural log of 4.
Yeah, I think you did that a little quick, but wait. So it would be 4 squared over 2.
16 over 2, so 8.
Yeah, minus the natural log of 4. And minus, I'm sorry, I didn't mean, I like love sleeping in. Also, I didn't mean to like wake you up early. So next time, feel free to be like, I want a later times. I could have met you slightly later if you needed.
No, I should be waking up earlier. That's fine.
No, but you have a very busy schedule, so I understand. Don't worry. So 8 minus the natural log of 4, and then minus 1 half, and then plus the natural log of 1. And what's the natural log of 1? Minus. Huh?
Is it E?
The natural log of e is 1. The natural log of 1 is? Yeah, the log of any log base of 1 is 0. Okay, cool. So, and you should see why it was a plus. I had to distribute that minus sign, blah, blah, blah. So now that's going to be 8 minus a half is 7.5 minus the natural log of 4. Fair?
Yeah.
Okay, cool. All right. So next page, we said we're not going to delete stuff. So, all right. So find the area of the region bounded by the parabolas, x equals minus y squared plus 4y. And I kind of like, on a quick scan of these questions, talk to you about how you could go about like, graphing these and such. So I'm going to let you do a lot more of the talking in this problem. So go ahead.
So on the first one, it's x.
Huh?
I'm trying to figure out how to.
I mean, don't overthink it. Just x and y axis are swapped. So if it was minus x squared plus 4x plus 5, you would have factored, and that's how you'd start with the zeros and such. So proceed the same way.
Yeah, I'm trying. I would say it's not a factor.
Huh, Brian?
It's not a factor.
It's okay. So hold on. Let's factor out a negative sign, and then it's going to be y minus y squared minus 4y minus 5. Lead me from there.
Y minus 4.
Y minus 5, I'll do this one. Y minus 5 times y plus 1. Okay. All right, so we set this equal to 0 since we're after the intercept, so the negative all the way in front goes away, so we get y equals 5, and y equals what? Yeah, we made x 0, because x is what's on the other side of the equal sign, so obviously what we found is 0, 5, and 0, -1 are the 2 points. Got it. So 0, 5 is like all the way up here. 0, -1 is down here. Uh, is it gonna face this way or is it gonna face the other way? You tell me.
The other way.
Yes. How did you figure that out?
Because it's negative.
Yes. Beautiful. Very well done. So we don't really care about. Yeah, we want to know where that point is. Blah blah blah. We could do minus b over 2a, but with y blah 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 to figure out what that is. But don't do more work than you need to. Maybe we don't need to do that. So because we're gonna guess that this other one is gonna look like that, so we know. Anyway, go ahead. So talk to me about this one now. You got it.
Y plus 5y
Hmm. I think that one is tricky. Maybe you're not. You're not. Yeah, it's not your factoring. Y plus 5. So we need two numbers that multiply to +5, but add to -4. What are all the numbers that multiply to +5? One and yeah. Either they're both negative or they're both positive. That's correct, right? Yeah, but then neither of them adds to -4. So this one, we have to complete the square. It's easy. So it's going to be like y squared minus 4y, split the 5 into +4, plus 1. Now this is a perfect square. Isn't it like y minus 2 all squared? Yes. And so plus 1. And so y minus 2 all squared plus 1 is has a vertex at 2, -1. So it's like here, and it's going to otherwise look something like that. Fair?
Yeah.
Okay. So I did this quick, but you'll get it. You get it. These are things that you know. Okay. Or just review. Okay. Sorry. I need to know how to erase whole page. But anyway. But we still have more work to do in this problem. What am I talking about? Huh? Well, sure. But before that. How do we figure out what like, so first of all, like, let's start writing our integral. So it's integral. Which one is on top? Which one do we subtract from which?
The one that's opening to the left.
So
The one that is subtracted from.
yeah, so we subtract this one, the second one we drew, this one from this one. Okay, so like basically in the order that they were given to us, basically that's how it worked out. So we do minus y squared plus 4y plus 5, crucial, minus parenthesis, because we're subtracting all of this. Okay, and y squared minus 4y plus 5, and then dy. Okay, got it. But then we have the all important limits of integration right there and there. How do we figure out what those are?
Where they intersect.
Yes, absolutely. Now note that I casually said this, but dy, because this time we're integrating along the y-axis. Okay. So yeah, that's right. So I'll get us started. Minus y squared. I mean, I'm not doing anything other than something you already know, which is setting them equal, but then you talk from there. So y squared minus 4y plus 5. Talk to me.
So it'd be -2y squared.
Yeah, that's good because, yeah, that's simplified nicely. Talk to me from here.
Then you divide that 2, so it'd be y squared plus 4y.
You go ahead.
Negative y squared plus 4y.
Or y squared minus 4y, either. Alternatively, you know, if you could just take out a -2 and be like y squared minus 4y and then divide by -2 after you do this factoring. But whatever, like I know this is a step you know. Okay, but if we go in the direction you wanted, where do I go from y squared minus 4y? That's right. My visual. Go ahead. Yep. Y equals 0. Mm-hmm. Go ahead. Sorry. Yeah, y equals 4. That's right. Now, so my visual is a little casual. Obviously, like I was being casual, but wait. But did we find that one of them had an intercept? Yeah, that's fine. They could still meet at 0. Like, yeah, basically in my drawing of the second graph, I should have been a bit more careful because that's really what it does. Because obviously, like, one of their intersections is 0. So I need to fix my we didn't draw the first graph incorrectly, and like why I paused is because you know like we had one of its intercepts a -1. That's perfectly fine. It's just the meeting point to be different from that. So anyway, now all you gotta do is throw on 0 right there, throw on 4 right there. The rest of the steps are pretty straightforward, but you know since this is like a hard second example, we can finish it together. So talk to me about the integral that we wrote, how to finish it. Mm-hmm. Mm-hmm. Exactly. And so from here, well, no, I don't need to write an integral anymore. We're ready to integrate. Go ahead. Yep, 8y squared over 2, which is good job. 4y squared. You simplified in your head. And then obviously, like this is 0 and 4. 0 annihilates everything, blah, blah, blah. We don't need to talk about this beyond here. Okay. Okay, so next is average value. So this is very important for the AP, which is not too far off. And so this is what you need to know. Average value different from average rate of change. I needn't even mention average rate of change because that's about derivatives. It's rate of change. So, but I'm just keying you into words to look out for when you sit for the AP. Average value, because they sound alike. Average value versus average rate of change. Average rate of change is about derivative. Average value is about integrals, and that's where we're at. So an average value is defined as 1 over b minus a, the integral from a to b of whatever function you're dealing with. Let's call it f of x dx. Okay, so here it says given the give the average value of y equals 2x minus x cubed. Notice that like you don't have to do area blah 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 in this question. It's simply asking you to apply the formula I wrote down, and it gave you a and b. X equals 0, x equals 4. So basically what I'm saying is beyond here I don't need to talk. You should be able to execute this all on your own. So talk to me. I'll write. Yeah, sure. F of x and y are the same. Yep. Mm-hmm. Yep, exactly. Talk and go ahead. Keep talking. Yep. Yep. No more dx. Vertical. Yeah, and like as far as the math syntax or whatever, this is the way you should write it. Continue talking. What's 4 cubed? Yep, 64 over 3. And obviously 0 annihilates both of the terms. And if we distribute the 4 right there and there, it simplifies a little bit. So the 16 turns into a 4 because we're dividing by 4 minus, if we just divide the 64 by 4 and then divide by 3, what's 64 divided by 4? That returns us to, I don't know, 4 squared, 16. Yeah, so minus 16 over 3. Mm-hmm. And so this, if we simplify common denominators, the 4 is 12 over 3. So we get negative 4 over 3, right? Yeah. Okay, cool, got it. Now, sorry. So yeah, we're done with this problem, but I was just thinking ahead to the next part because I read it earlier quickly. So B, so talk to me about B. Yeah, so what do you think? I would love for you to figure out how to do this part because like you have everything, although you know not adequate practice, you have all the tools necessary to figure it out. So what do you think we have to do here? Yes, but it's okay. Say more. So where it you said where it equals negative 4/3, right? So I'll write that part equals negative 4/3. But what goes on the left side? But what is the average value of that function? How do we find average value? Oh wait, sorry, hold on. At what point in the interval does the function assume its average value? Oh, I see, I see. You're right, you're right. So I was gonna write this like, and I think I overthought it. Like, look, I think you're right. Sorry, hold on. I was gonna write 1 over uh, x minus 0, but this doesn't make sense. 0 to x of, what was the function? 2x minus x squared. What you are telling me to do, and Ryan, is to do 2x minus x squared equals negative 4/3, right? You are correct. Why am I wrong if I had written that? Yeah, so what x would I find if I proceeded with that integral? Well, sorry. So because what we're trying to figure out is this x value, the upper limit. I would find that that's equal to 4 because the way we found that is by doing the average value from 0 to 4. So your thinking is right, my thinking is not. Like this is a quadratic he's asking you to solve. So if you multiply, I mean, I don't need, yeah, I think, do I need to talk more about how to solve that quadratic? Yeah. I don't think so either. Okay, so let's keep it moving in the interest of time. So find the volume of the solid generated when the region bounded by y arc of y equals sine x, and the x-axis is revolved about. So these are solids of revolution. Are you into video games at all? Yeah, I'm not. Obviously, at my age, I'm not. Like, but when I was like 13 or whatever, like I used to. I only want a few video games, and one of them is Metal Gear Solid. So Solids of Revolution reminds me of that. But anyway, I'm being really dumb. Trying to make you. I'm trying to make you laugh. But okay. So y equals because the main character's name is Solid Snake. He's my favorite all-time video game character. Anyway, y equals sine x and the x-axis, blah, blah, blah. So first, let me talk about this because you haven't talked about solids of revolution. Solids of revolution. And so there are 3 methods you're going to learn. Tuck away the 2 because they're probably not in this note sheet yet. Although Mr. Clark is crazy enough to put them on here. So one of them is the disk method, and the other, you will invariably learn about the others. The other is the washer method, and the third one is the cylindrical shells method. Okay, so anyway, like these two you'll learn about in the future. For now, let's focus on the disk method. So if you read the question he gave carefully, it says find the volume of the solid generated when the region bounded by one arc of y equals sine x around the x-axis. So first of all, he's like making the question really cool, which is he simply said one arc. He didn't say where. So one arc of and by doing that, he's implicitly suggesting that it doesn't matter which of the arcs of sine you decide to revolve, you'll get the same value. So like one arc of sine is that. So this is 0, and so where would that be if this is sine x? Exactly. And what Mr. Clark is suggesting again is if I take this dotted part, that still make one arc, only this would be negative pi. If instead you revolve this region, he's saying the volume would be the same as if you revolve this region. It's like, yeah, okay. But anyway, it's cool that he like subtly pointed that out. So like, let's shade this. So this is your first time doing the disk method with me. And so I'll try to like explain by using this example. So what you're doing is you're spinning this region about here. Now, let me quickly like, talk about the idea of revolving something about an axis. So suppose I take this triangular shape and I spin it about the x-axis. What solid would it form as it spins around? The triangle. Exactly, exactly. So for the sine function, it's like some like interesting, cool like solid that doesn't have a name, unlike the cone. But the point is that like you understand that as an area spins around an axis, it sweeps out a solid. And so the idea is you find the volume of the solid. Now, what's really cool about this method is this, right? So if instead of like revolving the whole region, we take like one thin line. Hold on, let me delete around it so you can see the line I'm spinning. If I take one thin line right here and I spun that line, then what I would have is a circle. You follow?
Yeah.
What would the radius of this circle be? Obviously, the radius is that r right there. But what would that radius be using, what we're given here? Yes, yes. Like awesome. Yes, if this is x, whatever x value it is, that radius is sine x. But the point I chose, where I drew that radius for that circle, it was arbitrarily chosen. So you can move like, to another bigger circle in this part, and it's still sine x for this time for whatever x we have right here. So the whole point is r is sine x. Other than that, what you're spinning are circles. So then the area of one of the generic circles, let's say that one, is pi r squared, because, well, the area of a circle is pi r squared. Only again, r is defined through the function sine x in this case. But wait, what you're doing is adding up a bunch of these circles, because look, if I take one circle, the one next to it, and the one next to it, and they were like infinitesimally close to each other, like they were arbitrarily close to each other, they would make my solid. It's kind of like if you like took a bunch of thin circular piece of paper of different sizes and put them together, they would form a solid. So that's kind of what's going on. But wait, in math, we say add using integral. So integral literally means add. I think we've talked about this. So what you have to do is go from 0 to pi, and then pi r squared. You're adding up circles, but it's along x, so you go dx. And so the only thing that you would have to figure out is how r is defined. So what function bounds r in all places. This time we know it's sine. So what we end up doing is the integral from 0 to pi of pi times sine x squared dx. Now I'm keeping our time constraints in mind, but let me know if I'm going too fast or you follow.
No, I'm following.
Awesome, beautiful, very well done. Now, so I want to say this, right? Like, so like real quick, like this is a preview to what's to come. But if you have sine x here, and let's say you have y equals x here, when you spin this around the x-axis, well, this time we must be talking about that because we're talking about two functions. So what happens is, like, if I take a generic cross section of the solid, if I slice the solid vertically at 1x, what I get is a washer. A washer is like a little metallic thing that looks like this. It has a hole in the middle, right? So then that's the washer method. That's like when you're spinning about a region where when you spin it, there's a hole in the middle of your solid, right? When there isn't a hole, like, so for these kinds of questions, you know that you're using the disk method. So I'm saying all this to say that, like, you can as soon as you know it's the disk method, right? Like, which is the first so many questions, you could immediately write down this formula. Integral from zero, not from zero necessarily, from a to b, whatever a and b are for the region, and then pi. But yeah, so the disk method, I'm saying, has a formula a to b pi r squared dx, and as long as you're spinning about the x-axis, it will never change. This is always the formula that you use as long as you're spinning about the x-axis. So the only thing that would change is you got to figure out what a and b are, and you got to figure out what r is for the specific function. Now, as far as executing the task, thanks, Mr. Clark. You like always make the questions interesting. Like, this is not an elementary integral. It's not very hard, but it's not an elementary integral because it's a Mr. Clark integral. So 0 to pi, and then we have pi sine squared dx. Sorry, sine squared x dx. Now, usually we use, like, the substitution method, blah, 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 to do integrals, or you just know them. Like, for polynomials, you figure them out. Sine squared, I'm saying, is not an easy one of those. So you have to do a little trick to integrate sine squared. I'll show it to you, though. So obviously, the pi, that pi, it's a constant, so I can throw it in front of the integral. And then we have 0 to pi and sine squared dx, sine squared x dx. So to integrate sine x or cosine x, blah, 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 obviously you can't just add 1 to the power, blah, blah, blah. You have to use this trick for sine squared and cosine squared. So please remember this trick. And it is appealing to the cosine double angle formula. So remember, cosine 2x is equal to, well, it's equal to three things. The one you'll need for this one is 1 minus 2 sine squared x. You see why? Yeah, well, okay, so I'll guide you. From here, isolate sine squared. So how would I isolate sine squared? If I isolate sine squared, there's a 2 right there. First, subtract the 1. I'll do it. You're still sleepy. It's okay. Cosine 2x minus 1 divided by negative 2 equals sine squared x. Now simplify. No, one of them is inside cosine, the other is just a constant. If there was a 2 right there, yeah, but, well, even if there was a 2 here, I need another 2 right there. Anyway, here's what I'm saying by simplify. Multiply both numerator and denominator by negative 1. That way we get rid of the negative. So it's going to be minus cosine 2x plus 1. So that I could write that with better math grammar as 1 minus cosine 2x. And then all over 2, that's the same as multiplying by 1/2 in front. So I'll choose to see it that way. Fair? Again, you have to come to the cosine double angle formula, cosine 2x, whenever you're integrating sine squared or cosine squared. Okay, so it's pretty clear why we want this replacement for sine squared. First of all, they're the same. Second of all, since we don't know how to integrate sine squared or cosine squared without this kind of a thing, but we know how to integrate cosine 2x, blah, 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 that's why we wanted to move in this direction. So the next thing you'd write is pi integral from 0 to pi. Sine squared is 1/2. I didn't need that parenthesis. Hold on. It's 1/2 1 minus cosine 2x dx. Now, this 1/2 I could get rid of right there and just write pi over 2 there. Fair? Okay, well you talk from here. My throat is literally hurting from like talking so loud. Go ahead.
So pi over 2 times n.
Yep, beautiful. Like I am so happy with like how you like know what you're supposed to know. Anyway, go ahead.
X minus the negative sign. Yeah, negative sign. 1/2.
We already took care of the one half. It's all the way. Oh, I see. I see. Yes, you're right. First of all, the minus sign just go ahead. Go ahead.
Minus 1/2 sine 2x.
Yes, beautiful. Very well done. What I'm really especially happy with is you didn't need u sub. Yes, you can make a mini u substitution and be like u equals 2x, and then du equals 2 dx, blah, blah, blah. Du over 2 equals dx. But if you did all that, all you would know is that like you needed to divide by 2 or right 1/2 right there, which you figured out all on your own. The derivative of sine is cosine, so that part you should have figured out. And so your first guess should have been sine 2x. But if I'm probably telling you stuff you know, but it's okay. Like if I differentiate, take the derivative of sine 2x, I'm gonna get cosine 2x. But by chain rule, I have to multiply by 2, and it is for that reason that we had to divide by 1/2, or multiply by 1/2, or divide by 2. Blah blah blah. Okay. So then otherwise, put a vertical bar here, put a 0 here, put a pi here, plug them in. I feel like you could do the plugging in on your own. Fair? Okay. All right, but listen. So the next two questions, problem 2 and 3, I could do them with you, but they don't. I wouldn't add as much as I did in this question, which is to say that like they're both about the disk method. So you would proceed the same way. Notice that in doing the disk method, it's really useful to have a general graph, blah blah blah. But otherwise, you want to use this formula: a to b pi r squared dx. Again, all you have to figure out is what are a and b, and then what is r in this specific case. So I would like you ahead of our next session to try problem 2 and 3. Feel free to like text it to me later today. I'll make time to look at it away from our session time and see how you did. But yeah, like you should use 2 and 3 as practice for you. Fair?
Yeah.
Okay. All right. I hope you have a wonderful day, and I'll end the session here.
Thank you.
You're very welcome. Bye.